Okay, our next piece is to figure out how we can use the notions of the calculus to work with these increasing, decreasing functions. Now, the first piece is, let's sort of draw a couple pictures here and see if we can get a feel for it. For now, let's assume that we're talking about the open interval A to B. It doesn't need to be an open interval. It doesn't need to be an interval of finite length. But for now, to make the pictures a little more straightforward, let's assume we're in the open interval from A to B. So here's my value A. Here's the value of B. And let's suppose that the function is increasing. All right. So there's an increasing function. So we say f is increasing on the interval A to B. If you want to write f is increasing on the interval A, B, these are the symbols you'd write. Anyone who knows what you're talking about knows those symbols mean that. All right, and then let's use another picture here. Here's A, here's B, and so here f appears to be decreasing on AB. So this is what our intuition tells us should be happening. And yes, if I choose x1 smaller than x2, then as we saw earlier, f of x1 here would be smaller than f of x2 here. Small x values correspond to small y values. Large x values correspond to large y values. Over here in this scenario, a small x value corresponds to a large y value. A large x value corresponds to a small y value. So in this case, it's reverse. Small goes to big, big goes to small. Here, small goes to small, large goes to large. So these match what we think we understand, and these are, this is an increasing function and a decreasing function. But now let's think about how that plays with the calculus. I think it's not too hard to see that. Consider the tangent lines to this increasing curve. If I were to draw several of them in, so at several different points, all those tangent lines have something in common. And in this scenario, on the decreasing curve, all those tangent lines have something in common. In this case, is it clear that all of these tangent lines have positive slope? The slope of the tangent line is positive. Whereas over here, for the decreasing function, it's not too hard to see, it's not too hard to convince ourselves, the slope of the tangent, slope of all the tangents, the slope of the tangent is negative. And in fact, that is exactly the issue, and this is the tool we're going to be able to use to analyze the increasing and decreasing portions of the function. Remember that slope of the tangent is calculus code for the derivative. And so in each of these scenarios, and whenever the function is increasing, the slope of the tangent is positive. That means the derivative evaluated at any point. If you are given any value in here, let's call this x. Any x value given here, f prime of x is bigger than 0. That's what we mean by the slope of the tangent. The derivative, positive, means greater than 0. Whereas in this scenario, given any x value here, that determines a tangent line. If this is my value x, then the slope of this tangent line is negative. That means it is less than 0. And so we're going to put this together into a statement, and I'm actually going to work through a bit of a proof to show that this statement actually is true. So let me get rid of this. And this is our statement. suppose we are given f of x is continuous on the closed interval a, b, and differentiable on the open interval from a to b. Now this should be familiar to us. This means that there's no holes, no jumps, no vertical asymptotes. Differentiable means there are no cusps. So this is a smooth curve. This is the same hypothesis we talked about in the earlier video, talking about the mean value theorem. So f is continuous on the closed interval, differentiable on the open interval. The differential means the derivative exists everywhere. If we're given any value in the interval, then we know the derivative actually exists there. Now, so given any, let me restate that. If we have we know the derivative of x is greater than 0 for all values in the interval. So we know the derivative is greater than 0 for all the values in the interval a to b. Then f is increasing on a to b. Now remember what that means. Let's translate this. Then if we are given x1 less than x number 2, what must be true? What must be true for this function to be increasing if we're given x1 less than x2? Well, we remember from earlier, that means that f of x1 and f of x2 must be related in a certain way. Remember that increasing means small x values go to small y values. So x1 less than x2 must mean f of x1 less than f of x2. Now what I want to do is work through a bit of a proof to show this statement actually is correct. What I'm going to do is show that this is true for suppose and then there is a similar statement for decreasing, which I'll write up afterward. So suppose we're given a continuous function on the closed interval, differentiable, and the open interval, and suppose we are given that for all values in the interval, the derivative is greater than 0. So here's A, here's B, all right? Now, we are given x1 less than x2. We want to show this statement is true. We'll show that if we are given these values, this must be true. Ultimately, this is what we want to establish. That's the piece we want to find, right? So, suppose we're given x1, x2. So here's x number 1, and here's x number 2. So we're given x1 less than x2. It is in this, each of these values are in this interval. So if the function is continuous and differentiable on the interval from a to b, it certainly is continuous and differentiable on the interval from x1 to x2. So we know that f of x is continuous not only on this interval, it's also continuous on this interval, x1 comma x2, and it's differentiable on the open interval from x1 to x2. So this function is continuous on this closed interval, differentiable on this open interval. What that means is we know that for this function, the mean value theorem applies to this little inner interval, this subinterval. The mean value theorem applies to this interval. So what do we know from that? The mean value theorem says this: if the function is continuous on the closed interval, differentiable on the open interval. Do we recall what that means? There must exist a c in this open interval, c between x1 and x2. Now let's suppose this is the graph of our function. So this is the slope of the secant line. There exists a c such that, do you remember what must be true? What must be true is the slope of the tangent at c must equal the slope of the secant between x1 and x2. So there is a c in x1, x2, and what must be true? The slope of the tangent line at c must be equal to the slope of the secant. Well, that's f of x2 minus f of x1. Remember, we're working on the interior interval, not the entire a to b. That's got to be over x2 minus x1. So we have a function's continuous on closed AB, differentiable on open AB. We know the derivative is positive. For every value in here, we know the derivative is positive. We know the derivative is positive at x1, at x2. We know the derivative is positive at c. For any value in here, we know the derivative is positive. That's given. We're also given that x1 is less than x2. Now think what that means. If x1, let's go over here to the side. If x1 is less than x2, that means we can subtract x1 to the right-hand side of that inequality. We can say 0 is less than x2 minus x1. But if we reverse the inequality, that's the same thing as saying x2 minus x1 is greater than 0. Something is greater than 0 means that is a positive expression. x2 minus x1 must be a positive number. What are we trying to show out of all this? We want to show the function is increasing. This is what ultimately we want to show. We want to demonstrate that f of x1 is smaller than f of x2. Well, look at what we have. We have f prime at c is something. It is equal to a fraction, which is something divided by something else. And we have all the pieces of the puzzle here if we know how to put them together. The first bit, we know f prime of c, the derivative is bigger than 0 for all values in this interval. For anything in here, the derivative is bigger than 0. In particular, c is in here, therefore f prime of c is bigger than 0. So that means this, something is bigger than 0 means it is positive. I'll just indicate that with POS. So we know the left-hand side of this equation is positive. Over here, we just established x2 minus x1 is greater than 0. It also is positive. And so we have it. We have a fraction, a numerator that we don't know about yet, divided by a positive number, and the answer is positive. Now we've known since basic algebra, the only way that can occur is if this numerator must then also be positive. If the numerator were negative, then negative divided by positive is not going to equal a positive value. So this numerator must also be positive. So from the given information, this necessarily implies that this must be positive. The numerator must be positive. That is to say, f of x2 minus f of x1 is positive. It is bigger than 0. What does that mean? That means I can add f of x1 to the right-hand side of that inequality, and we have f of x2 is greater than f of x1. Well, if A is bigger than B, then b must be the smaller than a. So f of x1 must be smaller than, I'm just going to reverse this inequality, must be smaller than f of x2. That's exactly what we were asked to show, which is to say, if we are given small x value and large x value, then f of the smaller is less than f of the larger. Small x values go to small y values, large x values go to large y values. So this is that necessarily means that we have met the condition for this function to be increasing. Therefore, f is increasing on AB. An exactly similar argument could be made for decreasing. We will assume that is done. And so yes, this is now becoming this will now be the method we will use to determine if a function is increasing or decreasing. A function is increasing on an open interval if the derivative is greater than 0 for all those values. That becomes the touchstone, the test that we will use to determine whether a function is increasing. F prime bigger than 0 means that the function is increasing. And similarly, f prime less than 0 means that the function is decreasing. So let's summarize that. This now is the takeaway for you guys. You don't need to be able to reproduce that argument until you go to graduate school, but that's up to you. All we need to have is this. Number one, f is increasing on AB for our purposes. Now, different textbooks do this differently. Different instructors do this differently. There are different ways to work this. What we're going to do for our work is we will talk about increasing on an open interval, not the closed, increasing on an open interval. F is increasing on an open interval if the derivative is greater than 0 for all x in AB. Second, f, this is the part we didn't prove but is correct. It is exactly similar to the argument I just made. F is decreasing on AB if f prime of x, that is to say the derivative, is less than 0 for all x in the interval. And then another piece we didn't discuss, but I think is clear, f is constant. It's a constant function on AB. Now, what does a constant function look like? Well, that's a horizontal line. For a linear function, the tangent line is the function. So the function is horizontal means that the tangent line is horizontal. It's the same line. So the function is constant on the closed interval if the derivative is equal to 0 for all x in the interval. So that's our takeaway. And what we're going to do is use this information and some algebra and some technique to be able to say, given a function, you now need to be able to go find the intervals on which the function is increasing, on which it's decreasing, and if there are any intervals where the function is constant. This is much more rare. Most of our work is going to be emphasizing these first two pieces here.